During this course, we're going to offer some short sessions on certain sections of the book that can be a little confusing for students. The first one we're going to look at is in Chapter 2, Set Theory, Section 2.4, Set Operations and Venn Diagrams with Three Sets. The objectives of this section are to perform set operations with three sets, to use Venn diagrams with three sets, and to use Venn diagrams to prove equality of sets. This is example 1. We're given 4 sets. We're given the universal set, and you can see the elements are listed, A, B, and C. And we're asked to find the intersection of A and the union of B and the complement of C. The little apostrophe by the C means complement, which is the elements in the universal set that are not in C. So first we're going to find the complement of C. We look at U and compare it with C, and we see that the complement of C, those elements in U that are not in C, are 1, 5, 8, and 9. Next, we work inside the parentheses. We find the union of B and the complement of C. So combining those two sets, we get 1, 2, 3, 5, 6, 8, and 9. And even if an element is in both of these sets, we only list it one time. Finally, we find the intersection. You can see on this first line of step 3 that we have all the elements of A listed and all the elements of B union complement of C. So finding the intersection, we find only those elements that are in both of the sets, which are 1, 2, 3, and 5. Next, we're actually going to look at the Venn diagrams. And this relates back to the example that we just saw. So we've got 3 sets. We have A represented by a circle, B represented by a circle, and C represented by a circle. The universal set is the entire, in this case, square. And then the part labeled 8, VIII, would be the elements that are in the universal set that are not in any of the 3 circles. So starting in the center, the darkest part, 5, this region represents elements that are common to sets A, or circle A, B, and C. Next, you see that there are 3 regions. They're a lighter blue. 2 represents those elements that are in A and B, but not in C. 4 would be those elements that are in A and C, but not in B. And 6 would be those elements that are in B and C, but not in A. Now we look at the regions in white. Note that those are only a part of each of the circles, A, B, and C. So region 1 represents the elements that are in A that are not in B or C. Region 3 represents those elements in the circle B or set B that are not in A or C. And region 7 is the set of elements that are in the circle C, but not in A or B. And finally, like I explained earlier, region 8 represents those elements in the universal set, the entire square, that are not in sets A, B, or C. Now we're going to look at example 2. This is determining sets from a Venn diagram with 3 intersecting sets. So we're going to use the Venn diagram that is provided on this slide to find the elements of A union B, B intersects C, the complement of C, and A intersect B intersects C. So you can see that in this little table below, we have written the 5 different things we want to find. Then we have a description of the set. A represents a set of elements in A. And so referring to the Venn diagram, we see that the elements in A are in regions 1, 2, 4, and 5. So writing those in roster form, which means that you list all the elements, we have 11, 3, 12, 6, 5, and 7. And typically, when you have completed this problem, you would write them in numerical order, going from the smallest to the largest. Okay, we do the same thing for A union B. These are the set of elements that are in A or B or both. Well, these are the regions 1, 2, 3, 4, 5, and 6. So listing the elements in roster form, we have 11, 3, 12, 1, 2, 10, 6, 7, sorry, I missed 5, 5, 7, 9. And we do this for each of these. B intersects C are the set of elements are in both B and C in the intersection, which would be in regions 5 and 6. And the elements in roster form would be 5, 7, and 9. The complement of C would be those elements that are not in C, but they are in U. Those would be in the regions 1, 2, 3, and 8. You can see them listed here. And finally, the intersection of A and B, and then with C. So those would be the region 5, the darker area in the center, which are 5 and 7. In example 3, we're proving the equality of sets. So we want to prove that the complement of A intersect B is equal to the complement of A union complement of B. Notice that one is intersection, the other is union. We can apply deductive reasoning using a Venn diagram to prove that the statement is true. If both sets represent the same regions in the diagram, then this proves that they are equal. And that's exactly what we're going to do. So we want to prove that the complement of A intersect B is equal to the complement of A union complement of B. So we're first going to start with the regions represented by the complement of A intersect B. A has the regions 1 and 2, B has the regions 2 and 3. The intersection of A and B would be the dark region 2. So the complement would be those that are not in region 2, which would be 1, 3, and don't forget region 4 out of the universal set. Next, we want to find the regions represented by the complement of A union complement of B. So we need to find the complement of A, which would be everything not in A, which would be region 3 and 4. Same with the complement of B. It'd be everything not in B, which would be regions 1 and 4. So the union of those two would be 1, 3, and 4. Then if we look back at the preceding slide and this slide and the tables on both of the slides, we see that these are representing the same regions, so this proves that they are equal. Finally, De Morgan's law. This is just another way of saying what we just proved. The complement of A intersect B is equal to the complement of A union complement of B. And the complement of A union B is equal to the complement of A intersect the complement of B. We proved one of these, you can prove both of them by the same process. And that concludes this particular section in your book. I hope this helped you understand.